We should do for software what interchangeable parts did for mechanical engineering. Nicolaus Wirth, the creator of Pascal programming language. The Industrial Revolution brought with it a concept that forever transformed the manufacturing world, the idea of standardized, interchangeable parts. This notion, previously unheard of, allowed machines to be constructed from components that could be produced en masse and replaced effortlessly. Fast forward a few centuries, and we find the digital realm echoing this sentiment with its own paradigm shift: the rise of modularity in software design. Modularity, at its core, is the degree to which a system's components may be separated and recombined. It stems from an inherent human inclination to break problems down into manageable, comprehensible parts, a tendency that has governed us from the pyramids of Egypt to the modular homes of the modern age. In the context of software engineering, modularity refers to the design principle of organizing code into distinct modules or components, each responsible for a specific functionality or feature. These modules are relatively independent and can function autonomously, yet when combined, they form a cohesive, well-functioning software product. The essential tenet of modularity is the encapsulation of code, ensuring that the internal workings of a module are hidden, while only the necessary interfaces are exposed for other modules to interact. At its inception, the software was a relatively simple entity. Early programmers dealt with few lines of code, directly managing machine operations. But as the digital age matured, so too did the complexity of software. Projects grew, teams expanded, and systems became intricate behemoths, demanding a need for structure, organization, and a scalable approach to development. Modularity responded to this call by providing a framework that facilitates scalability and maintenance. When code is modular, individual components can be developed, tested, and debugged in isolation. This isolation means that the impact of changes in one module doesn't reverberate uncontrollably through the entire system, a safety net for developers and a guard against the domino effect of errors. Moreover, as software development increasingly became a collaborative endeavor, modularity enabled teams to work concurrently on different parts of a project. Imagine a group of architects working on a grand edifice, each focusing on their specialized area, yet aware that their work must seamlessly integrate into the larger structure. The software, in its modular architecture, mirrors this collaboration. Lastly, the very fabric of modern-day software innovation, open source projects, libraries, and frameworks, owes its existence to modularity. The reuse and sharing of modules have not only accelerated software development, but have also nurtured a community of collaboration and collective progress. In essence, modularity, with its structured approach, has been instrumental in elevating software from rudimentary operations to sophisticated systems that underpin our digital world. The way we build, maintain, and innovate in the realm of software is intimately tied to this guiding principle of modular design. Modularity in software offers a myriad of benefits that span across development stages and project lifecycle. One of the primary advantages is maintainability. With each piece of functionality neatly encapsulated within its own module, identifying and fixing defects becomes a more streamlined process. When a system breaks down into well-defined segments, developers can update or adjust a particular segment without unraveling the entire system. Alongside maintainability, the beauty of reusability emerges. Consider a scenario where a developer crafts a module for one application. If designed with modularity in mind, this same module could seamlessly fit into another application, significantly reducing both redundancy and development time. Scalability is another facet where modularity shines. As businesses grow and technology evolves, software solutions need to adapt. With a modular architecture, new functionalities can be integrated or existing ones can be enhanced without causing widespread disruptions. Furthermore, in the world of collaborative software development, modularity supports parallel development. Different teams or team members can simultaneously delve into separate modules, thereby increasing the speed and efficiency of development. This collaborative approach can be likened to an orchestra where each musician plays a distinct instrument, yet together they produce harmonious music. Lastly, flexibility stands out as a hallmark advantage of modularity. Given that modules have clear interfaces and encapsulated functionalities, it becomes less daunting to replace or upgrade specific modules without initiating a complete overhaul of the system. The concept of modularity is consistent, yet its application takes on various forms depending on the architectural approach. For instance, in object-oriented programming, OOP, a prevalent paradigm in languages like Java and C++, modularity is championed through the use of classes and objects. Here, an intricate dance of data and functions occurs within objects, with classes setting the stage as the defining blueprint. On another spectrum lies the service-oriented architecture, SOA, where software is deconstructed into services. These are self-contained units of functionality that communicate via standardized protocols. The analogy of a city's utilities serves well here. While water, electricity, and gas operate as distinct entities, they come together to ensure the city's smooth operation. Microservices is an advanced iteration of SOA, breaking software down even further into minute specific services. Each can be nurtured, deployed, and scaled independently, much like individual cogs in an expansive machine. Lastly, the realm of functional programming introduces yet another flavor of modularity. In this space, languages like Haskell and Erlang emphasize functions as the principal modules and champion the sanctity of immutable data, drawing parallels to the purity of mathematical equations. The journey of modularity is enriched when grounded in best practices. Cohesion is a cornerstone here, emphasizing that a module should ideally handle a singular, specific responsibility. Such a singular focus augments both reusability and maintainability. Additionally, the principle of loose coupling takes prominence. For modules to truly stand as individual entities, their interdependence should be minimal, predominantly occurring through intuitive and well-defined interfaces. Encapsulation further solidifies the modular foundation. By shielding the inner workings of a module and only exposing the indispensable components, modules remain guarded against external disruptions. Moreover, to foster integration and collaboration between modules, designing consistent interfaces is crucial. Such consistency makes it easier for modules to converse and collaborate. A significant aspect of modularity revolves around evolution. As modules transform, it's imperative to have a robust versioning system in place, ensuring a harmonious coexistence of modules and their dependencies. Navigating the modular landscape isn't devoid of challenges. Integration stands out as a primary concern. With a multitude of modules in play, ensuring a seamless synergy between them demands meticulous design and testing. The very structure that promises order can, at times, become a source of overhead. Managing diverse modules, orchestrating their interactions, and overseeing their versions can add layers of complexity. Striking the right balance in granularity poses another challenge. Too fine-grained a system might become cumbersome to handle, while a coarse one might dilute the essence of modularity. Dependency management further complicates the modular journey. As software ecosystems flourish, keeping track of interdependencies between modules becomes an intricate task, demanding diligence and foresight. Navigating the realm of modularity becomes markedly more accessible with the right set of tools. Integrated development environments like Eclipse and IntelliJ IDEA are tailored to aid developers in modular programming. Their functionalities span from dependency detection to ensuring the sanctity of interfaces, promoting efficient modular development. In tandem with IDEs, version control systems such as Git stand as pillars in managing modular software. They empower developers to monitor alterations, administer module versions, and guarantee that diverse modules harmoniously integrate, even when developed by disparate teams. Dependency management is another realm that cannot be overlooked in modular software. Tools like Maven for Java or NPM for JavaScript rise to prominence here. They automate tasks like fetching, updating, and incorporating diverse software modules. Their prowess ensures not only the presence of the right versions, but also their compatibility. Lastly, the modular world is further enriched by containers and orchestration systems like Docker and Kubernetes. Especially pertinent in the world of microservices, these tools encapsulate modules, ensuring a pristine environment for each and orchestrating the symphony of interactions amongst them. Java's evolution offers an intriguing lens into the world of modularity. With the Java Platform Module System, introduced in Java 9 as an offshoot of the Jigsaw project, Java took a giant leap towards embracing modularity. Before this, Java applications grappled with issues like the jar hell, primarily due to conflicting Java archive files. But JPMS transformed this scenario. The JDK was segmented into finer modules, enabling developers to selectively integrate them, leading to reduced application sizes and minimized conflicts. Shifting the spotlight to the entertainment sector, Netflix's software journey is a testament to the power of modularity. Initially structured as a monolithic entity, Netflix transitioned to a microservices architecture, a move that was instrumental in catering to its burgeoning global audience. Individual functionalities could be scaled in isolation, ensuring that a spike in one domain, such as account registrations, wouldn't hinder other areas like content streaming. In the domain of operating systems, the Linux kernel stands out as a modular marvel. Contrary to a monolithic structure, Linux boasts a core kernel complemented by a plethora of loadable modules. This design endows it with unparalleled flexibility, allowing its deployment across diverse devices, from colossal supercomputers to the compact wristwatches of today. The roadmap of software development is irrefutably aligned with modularity, with future trajectories pointing towards an even profound association. As the world gears up for an explosion in IoT devices, decentralizes computing, and embraces globally distributed systems, modularity's role will be pivotal. Modular designs inherently champion adaptability, resilience, and scalability, attributes that will be non-negotiable in these futuristic scenarios. Moreover, the confluence of machine learning and modularity could pave the way for enhanced software development. Algorithms might aid developers in demarcating optimal module boundaries or even preempt potential integration challenges. The horizon also promises an evolution of tools facilitating modularity. With the escalating intricacy of cloud platforms and the push towards decentralized computing, tools accentuating modular design, deployment, and scaling will ascend in importance. Embarking on a retrospective journey, one realizes that modularity, a concept rooted deep in software's history, is set to sculpt its future. By transforming complexity into digestible, cohesive segments, modularity becomes the linchpin for innovation, scalability, and maintainability. As the tendrils of software reach out to touch every facet of contemporary life, modularity's principles will guide this expansion. It's more than a methodology, it's the very philosophy that will mold the future ethos of software engineering.